My experience is if I put out the exam right now, you can kiss the lecture goodbye. It just doesn't even matter. And obviously we missed Monday. What can I say? Remember, I was worried about half the lecture. Now we're 1.5 lectures behind. We'll have to make it up somehow, which probably means it's Saturday. But hey, let's cross our fingers that doesn't happen. You know, and as I said before, you don't have to come to the Saturday lecture, right? You don't have to. Do whatever you want to do. You're an adult. You feel like an adult. A couple of things here that I want to talk about here is that, what did I finish off? Did I finish off example 6.3 where I had the summing amplifier? My memory tells me that I did not complete it completely. Is that correct? We got V out, but we didn't talk about the current. Okay, so how about if we do it from scratch? And just it's probably a good way to, for memory sake at least. Oh, by the way, I was rummaging through my office, and I found an old T-shirt. Look at this one, right? Does that look familiar right there? Hey. Evidence searches. And then, of course, the back. That's probably some stupid thing that I said in lecture. Hey, that's a T-shirt right there. I got to find that Supernote T-shirt. I thought the Supernote T-shirt was bad, right? Calling me the Supernote. I like that one. But I was just laughing that I found that this morning. I go like, but I'm not like Marcus, right? Marcus likes to put shit on his T-shirt. I always comment on Marcus's T-shirt. And he calls me the geek. Even has the beer sauce. What's up with that? Damn. And here we go. So, you know, it would be nice if I could get the computer or the monitor to turn on. I came in earlier this morning. I've already put a work order for that to get it to finish, but if you push the power button by hand, it doesn't work anymore. It used to work that way. But, so it would be nice to have it for this part of the lab, part of the lecture, but we're not going to have it. So, here we go. So, we started off with the circuit here. And one of the things that we talked about is that you could always use node or you can sort of like feel your way through the circuit. And so one of the things that I always encourage you to do here is stop trying to use those big, techniques that we have, where it's sort of like, your brain turns off. I know some of you like that. We like to make it hurt a little bit and have you think for a change. Right? So what we had here is we had this circuit here. And I think everything was 6K. And our goal here was to find two things here. We wanted to find the current going this way and the voltage drop across here. So when I look at this thing here, there's lots of ways to do this. And a lot of times people forget source transformations. Yeah, people forgot, like on that Thevenin problem. I mean, I think there was 2 people out of 44 that did source transformations and got it really into 2 really nice loops. And they did their problem in half a page. The rest of you decided to squeeze in 2 pages on one and then squeezed another 2 pages on the back. I bet that took a lot of time. And in this case here, I would never do it the way I'm going to do it right now. Right? And the reason why is that I want to keep getting you to keep thinking to sort of like follow the current. See where the current or the voltage is going to be playing a part here. What I would do here is that I would immediately do a source transformation. I would combine this resistor, I get another source transformation back, so I'd have a voltage and one resistor right here. Right, and I think I said that last time. That would be the way to do it here. But let's not do it this way, because I probably am not going to give you a circuit like that on a quiz on Monday. So you should be looking something like this here. So if I immediately apply simple circuits and the ideal op-amp conditions, well, I'm really seeing something like this here. So if I look at this, we clearly have this node right here. So that's 12 volts. So when I look at this 12 volts, what I'm seeing here is that I'm seeing this 6, and then when you look at this 6 and that 6, there's something really interesting. Because if you look here, that means that this guy is grounded, which means that this guy is grounded. So if those two are grounded, then I'm really looking at the current doing what? Going through this, it's going to split, but they're both going to ground. So that means that these two resistors must be in parallel. And if they're in parallel, that means I can find the voltage across this resistor. So if I find the voltage across this resistor, I know the current here, I know the current here, and therefore I know the current here because there's no current drop here. And so all of a sudden what I'm seeing here is that I expect that at this node right here, negative voltage. Why a negative voltage? Because if I'm having current that's moving in this direction and it's going from ground to that node right there, that means it's always moving from high to low. So if I follow the current, what am I actually seeing? I'm seeing the current go this way. There's a part of the current that's going to, go across that thing. So we could say that this is the current across the 6K. We said earlier that this is the current across these two in parallel, which being the current of the 3K here. So that means that since there's the current of this branch is 0 here, then that means that the current across this guy must be the current across the 3K resistor. So let's do this here. So if I look at this, what is going on here, I'm going to see here, so I'm going to calculate the voltage across the 3K. What do I mean by the voltage across the 3K? Well, it looks like this. And I could use voltage divider rule. So I know that's a 3 ohm resistor, or 3K resistor. So then, if I use VDR, that tells me that the voltage across the 3K must be 3K divided by the sum of these guys here. And so we're getting what? 3, 9, that's a third. So that should give me 4 volts. So now I've got the voltage across this guy. But if I got the voltage across that guy, I look at that 1 6K resistor now. I know that this is ground right here. And I know that this node right here has to be what? 4 volts. So that means when I look at the current going in this direction here, the current, what I call the 3K, we can see here that the voltage, that the current across the 3K resistor must be this. So therefore it has to be 2/3 milliamp going along here. But if I know that this is 2/3 milliamp, then I know that I could then calculate V out. So from this picture here, so now we can calculate V out via Ohm's law. Right? And so that means here, so if I look at this 6K here, you can see that it's attached to V out. And so if this guy is now ground, so then I'm just going to use Ohm's law. So So Ohm's law says that 0 minus V out divided by, times 6I of the 3K, then gives me that V out. So then that V out right away tells us that it's negative, as we expected. And then I get 6 times 2/3 will then give me negative 4 volts. Now note, I didn't have to do that calculation. Why didn't I have to do that calculation? By the way, if you were to have used words and not do this, I would have been like, right on, dude. Because, look, if I calculated this was 4, and it has that current, if I have the same current and that's that ground, it has to be 4. But we already knew that it was going negative, so if you just said, hey, that voltage here has to be the same as that voltage because of the current. So I could have come over and said, that's 4, okay, 4. But there's a negative sign because it's going down that. That would have been a complete calculation. Okay, now note, I did a lot of writing because that's what I'm supposed to do, right? To make sure that you follow all my steps. I never would have done this if I was calculating like this. I would have gone like this. I would have noticed that. I would have done this. I would have done that calculation. And then physically I would have said, well, that's got to be 4 also. Negative 4. So I would have gone from here to there, and it would have been done. But you want the non-thinking way. Right? We just want to say, as they say in the business, right? Just calculate and shut up, right? There's no thinking here. It's just. And I agree that, node can be very comforting. So when you look at this guy here, we know that all of these guys are 6K. No, I didn't calculate the current, but we'll calculate the current in this one right here. So if I look at this guy here, what do I know here? Well, note I can't write, right? You can't write this as a node equation. Cannot. Why is it? Because remember, this is the voltage value. It's like, so if you have something like this and this guy's, let's say, well, we already know that this guy's going to be negative 4 volts from our previous calculation. It's like trying to write that as a node equation. You can't. It's not a node. That's a node. That's a node. So we can't write this here. And I caught a lot of people in the PLC yesterday writing this as a node. So you got to be aware of that. So then I just start calculating my weight. No, that's 12 volts. It's really, there's only really 2 nodes. So if I look at this node, I got that node and I got that node. Let's just calculate all these, I don't know, how about A and B? So I do have 3 equations and 3 unknowns. Well, we know that that node's going to be the same. But you don't do it until afterwards. So let's do that. So now let's start with node A. So node A says that I have what? 3 resistors. And then I have 1 connected to 12. And 1 connected to VB. So if I do that, I know I probably should have called that VC, but we know that that's already grounded. So I'm just going to make it 2. And then I come back to node B, and you can see that B has 2. And then I have 1 with A, and 1 with the output. So if you look at this, this is what? 2 equations, 3 unknowns. Okay, so it doesn't work. And if my unknowns are these guys.
Can't you write an equation for the ideal condition?
Yeah, which is what I'm going to do right now. So then I apply the ideal conditions, or condition in this case, and then it says that VA must be the same as VB. But we know that this is already connected to ground. Maybe I should have called this VC. So I made a mistake here. We know that this is 0 here. So that really gives me that third equation. So if that gives me 0, I could then come back in here and I could do what? Well, I can get rid of that. That's 0. I can get rid of this. That's 0. So now, when you look at this, I now have what? 2 equations and 2 unknowns. So I'm going to let you do this on your own here. So now I can solve for V out. And you can see that this calculation is fairly straightforward, because you can see that V out and A here, well, that's really just tells me that V out has to equal minus A. So then I just solve for A here, multiply everything by 6, and you're going to get 3VA minus 12 gives me VA equal to 4. Then 4 then comes into here, and I get that V out is equal to minus 4 volts. Yeah, once again, let me ride you a little bit longer. Did you really figure out what was going on the circuit by doing this? I know this is very soothing and comforting. Yeah. Not the way to do it. Now, unfortunately, since we don't have the monitor that we can use here, I'll have to draw this on the board. So let's play with this next circuit right here. Okay, so this will be example 4. Oh, shoot, I forgot about the current. Thank you very much. So if I got to solve for the current, so the current that we're talking about is the current going like this. Now note, it's customary to actually write this always into the node. All currents, if you look at PSPACs, they're always going into the nodes of all of the sources here. So when I look at this guy here, well, if I just apply KCL, we see that we had what? We had one current coming in. We already knew that this was 2/3. Now, let's think about this current here. How did I get 2/3? 2/3 had a drop of what? 4 volts. So all the drops, so that means this guy here has to have a drop of 4 volts. Well, which we already knew about that. So, but if I look at this guy here, that 4-volt drop here, if this is negative, and this is 0, which direction is it current? It's going upwards. So if I look at this current is then going up like this, but that means here, because it's still that same 4-volt drop, it's got to be also what? Now note, I didn't put a minus on. I could, but it makes sense to keep everything positive. And then I have I out now, which is going like this here. And you can see, according to KCL, the sum of these two currents equals that, so it's got to be what? 4/3 milliamp for the current. So if I look at this here, then I out must be twice one of these, which then gives me 4/3 milliamp for the current. Okay, let's do this next example. You know, I was telling the guys yesterday in the PLCs, some of the people that I was sitting around, that exam cost me a lot in grade 9, because I actually tried to follow all of your mistakes, which drove me goddamn mad. And so I was telling the people at the table, you have to pay for my alcohol from all that grading, because I needed a lot of soothing as I was going like, son of a bitch, why did you do that? And then I just started writing. Now, I'm only talking to myself, of course, right? I would never call you that. I mean, it's not to your face, right? So, let's do this next circuit. So if I do this next circuit here, this circuit is made to force you to look at what is going on in the circuit. Okay? In fact, you can do no, but I'm probably going to skip it. I want to think your way through the circuit here. So let's go through this circuit. So it's a pretty intimidating circuit in the beginning. So all of the resistors are the same, and I think they're all 10K. Make sure I get my polarity right. And this is a 10 volt, and this is terminal. So then this guy comes out here.
Is the resistor at the bottom right hand corner?
Yes, thank you. So they're all 10Ks. So what we're looking at is that I'm asking for two things here. I'm asking for the currents. And since I ended up calling this guy 1, so I'm going to say this is the output current 1. And this is the output current 2. Just calling this guy 2 and this one 1. And then what I want here is that I want this voltage value like this. Okay. Let me give you a minute. Try to do this. Try to follow your way through the current here. No, it goes through the resistor. I mean, it does touch, right? You're talking about this guy right here?
Yeah.
No, there's a no.
Oh, it wasn't broken in the.
Does it look broken?
Yeah.
I can't really see, so it's not supposed to be broken. No, if it's broken, you'll see me do a little loop around. Okay.
No, it's like an idea.
Yeah, for sure. And then you called that one. No, I installed like. So you got one.
We know this is 10 because he's
Oh, that's why
I tried to run in here. Oh, sure. I really like one
Hey, let's look at this guy. So for starters here, I'm gonna, just for simplicity's sake, I wanna put in some nodes here that are nice and clean. So the first thing I'll do here is that it seems like I'll call this guy A, B, C, D, E. Okay, so if I have these guys here, let's sort of like, now let's look at the op amp here. So if I just start with sort of like following the circuit, one of the things that I see right away here is that if this is 10, that has to be 10. So immediately, this tells me here, so if I look at op amp 1, that immediately tells me that if VE is 10 volts, then VC has to be 10 volts. But if VC is 10 volts, then automatically VA has to be 10 volts. So just by looking at this thing, it's I got a lot of information here. But wait a minute. If this is 10 volts, we know that the current must be going down, right? That current must be going down. What is that current? Well, if that's 10 volts divided by 10K, it's got to be 1 milliamp. So here I go. So I'm just, so no, I didn't, right? There's no fancy calculations. This isn't supposed to be for fancy calculations. This is for trying to see what's going on. No current here. If there's no current here, that means that the current here must be what? 1 million. Right? 1 million. But if there's, so if there's no current here, there's no current here, then there is a current here. But what can I say about any of these other ones here? Well, I can get this node voltage because I know that node voltage. So then if I apply at node B, maybe I should write it here, at node B, look at Ohm's law. So then that tells me that VB minus VA must be 1 milliamp. So if this is 10 here, right, so then that tells me that VB, oh yes, sorry about that.
Why were you able to say that that top resistor had 1 milliamp going through it? Do we know the voltage of the?
Well, we know that there's no current here.
Yeah.
So
Oh,
that
right.
current has to be flowing in this direction.
Gotcha.
So then that tells me here that VB is the same as VO1. So then this tells me here if this is 10, then this means that when I bring this over, VA is also 10. So I get 10 plus 10 gives me 20 volts. I got that value fairly quickly just by stepping through this whole process. So how do I get the, what about this current right here? Do I know what this current is?
Yes.
What is that current? Which direction is it going? Why is it going that way? Well, if you know that this is 20 and you know this is 10, it has to go this way. So let's switch colors here. So then I know that because this is 20 volts and this is 10 volts, I gotta have 1 milliamp going that way. But if I got 1 milliamp going that way, we know that there's no current here, or current in this branch, so therefore I got 1 milliamp going there. So I haven't done very much, have I? But we do know one thing here. Let's just keep thinking our way through this. If this is 20, and this is 10, and this is 1 milliamp, that has to be what? 0. It has to be ground. That's the only way I can continue to have 1 milliamp in this direction. So that means here, right away, that has to be ground. But wait a minute, if that's ground, and this is 10, you can see that this guy has to be what? 1 milliamp right away. So what's the current going down here? So if I look at this current going down here, which is this I2, you can see from KCL, it's got to be 1 plus 1 gives me 2 milliamps. With almost 0 work here. And now if I want this voltage here, well, what's the voltage here? So do we know what VO2 is? 0. Right, so I could come right over here. I could say that by KCL, maybe I should say this, from KCL and ideal conditions, we conclude that VO2 must be 0 volts. Right? Must be at ground. So the only thing we got to do here is that I got the current here, so then I got to look at this current here. So what's this current? You can see here, if this is 1 milliamp, and that's another milliamp, I'm then going to apply KCL at node B. And what I see at node B here is that I have a current like this, where this is 1 milliamp, 1 milliamp, and this is I01. KCL then implies that it has to be what? Negative 2 milliamps. So by inspection, it has to be minus 2 milliamps. So I got the current and I got the voltage. Now, we could write this as a, node voltages, right? Excuse me, and write down node equations for these, but this wasn't supposed to be that type of circuit. So if you were to look at my lecture notes, you'll see that I did do it in node. So here's where we're being hurt by the computer, because now what we want to do here is we sort of like want to model a circuit so that it gives a certain output. And unfortunately, I can't show you. You could just Google, that's what I would have done. I would have gone in, I would have Googled op-amp circuits, and then you would have gotten a list. And then I would have showed you an image, and it tells you what each op-amp does. Like, you already know that the voltage divider, excuse me, not the voltage divider, the voltage follower, what does it do? It forces the output and the input to be exactly the same. If you remember the other one, the non-inverting amplifier, what did we know about the non-inverting amplifier? So, for example, so what we want to look at here is we want to talk about designing op-amp circuits. Give specific, output. Output quantity. And sometimes you'll see that we're talking about currents or we're talking about output voltages. That's what we're specifically doing here. So what I mean by that here, if you look at what we did in lab here, there's an inverting, excuse me, I think it's a non-inverting. Oh, I didn't do very good at spelling now. What a shock here. And when you look at this non-inverting amplifier, what we ended up doing here is that we ended up doing what? We put a source in one of the outputs like this here. So if I have a source like this, and then what we did here is that we put resistors into this circuit. And what we did here is that the key thing here is that now we have a resistor here, and this is typically called the feedback resistor, and then we can just call this R1 for right now. And so when I design a circuit like this, so I know that if I put it in this specific orientation, that V out is always going to be this guy right here. So what this means here is that we could do this. Let's say I wanted a 12 volt output. Okay, if I wanted a 12 volt output, so suppose we want a 12 volt output. What would I automatically do? Well, I could choose any combination of resistors. So let's say that I look in my toolbox and I find out that I have RF equals to 2K and R1 equals to 1K. So just looking at the circuit here, this implies here that the gain of the circuit, right? This is what we mean by the gain. The gain of the circuit here is clearly 1 plus 2 over 1, which is 3. So it has a gain of 3, and it would be volt to volt. So if I do that, then that means if I set my input to 4 volts, then clearly my output has to be 3 times V in, which then guarantees that I get a 12 volt output. So which, I mean, it's not like I had to, like, you already knew this, but what I'm saying here is that now we want to use output values that are very specific. Maybe it's running, I don't know, maybe it's one of the force sensors in the physics lab. Or maybe it's, the force sensors in the physics lab, I think what they do here is that they measure in microvolts. But in order for the, the computer to pick it up, I think they gain it up to about 100,000. So therefore, they're measuring about 1/10 of a volt. So what you're finding here is that it measures in microvolts, and then it amplifies it so that now it's at a value of 1/10 of a volt. So how do you do that? Well, you typically, one way that you can do that is that you can set up op amps where you just sort of like start clicking things in. Almost like the Arduino type thing. You want something to happen, you plug it in, and then you get this output. Op amps operate exactly the same way. Like I said, if I could have use of this computer, it would be really helpful. But let's look at this circuit to give you an idea, because you do have some of the homework problems that ask you to do this. And what I want you to do here is that when you're looking at your problem sets, when you're trying to design some of these op-amp circuits, just try to look at the page on Google or whatever it is that you want to look at, and just see what combination can I use to actually get this. And so what I was looking at here is that I was looking at example 6.5. And all we know is that we have 2 inputs. And we're talking about some op-amp circuit here that we want to design here. And we want to have, over this 20K, we want an output voltage that's equal exactly to I'm sorry, that we want to find out. I made a mistake here. We want the output voltage so that it's V1, V2 gives me this specific combination like this. So I want, for some strange reason, we got this op-amp circuit that you need the output voltage to be exactly like this. So here's the inputs. Then they say design the op-amp circuit, how to do that. Now since I can't show you what's there, what I want to do here is that I need to look at this circuit here, and what you're seeing here is that I'm doing what? I'm taking these two voltages, and somehow it looks like I'm subtracting them. But I'm not really subtracting them. I'm summing these two voltages. And then, somehow, I gotta come in and I gotta change the sign of one of these guys. Yes?
On my sheet, there's a ground sticking out of the bottom of the op-amp circuit. Is that supposed to be there, or?
Sure. I can put it on. Yeah, the ground, just remember, all of these are grounded. If this is our sources, there's a ground here that I'm not showing you either. So the ground doesn't really matter, it's sort of like, we know that it's there, because everything has to be measured relative to this. So what I want to do here is that one thing that I can do here is that I can use a summing amplifier. And then what I want to do here is that after I sum the voltages, I could run one of these outputs so that it makes it negative. And what makes something negative is now to make one of these negative. Okay, so you can see that the one that's negative is 2. So I'm going to run wire 2 into an inverting amplifier. So now I'm going to run V2 through a inverting op-amp. And like I said here, that sheet, on Google will just say, okay, what do I mean by summing them? So what I mean by a sum here is that I can have there's a couple of things here. So if I do a summing amplifier, it turns out that the summing amplifier automatically gives you a negative sign. So if I look at the summing op-amp, what you're going to find here is that it looks something like this. So I have a circuit that looks like this. It has a feedback resistor. And this feedback resistor now has 2 lines. And I could call this R1 and I could call this R2. And when I sum these guys, what you'll find here, and note everything's relative to ground here, when I sum these, and one of the ways you can find out whether it's inverting or not is that look at pin 5, the pin to the positive input. That's connected to the ground. So that typically switches the sign on these guys. And so what it does here is that it does the following thing here. Is it says that this V output is equal then to the sum of the feedback over R1 times V1 minus RF V2. That's what that summing amplifier does. So if I was to factor out this minus sign, it sums these two, but it's inverting it because of this guy right here. Now if I do that, By the way, why does this invert the sign? Can you physically tell me why it inverts the sign?
Because the positive is at ground.
Yeah, but why does that make that, give it a negative sign? Look at the current. Follow the current. Right? If you follow the current, you notice there can't be current going into here. So if you follow the current here, note that this is automatically ground. So as I follow the current has to go this way, so you can see that that ground forces this guy to be negative. Therefore the negative sign. Yes, I have KCL with these two at that node, but then once I get the current here, it forces it negative right here. That's why they call it an inverting amplifier there. So what I can do here is that typically what I'll do here is that I can call this V1, V2, and so now I can sum these two, but the cost is what? I'm going to get that negative sign. So now, to get rid of that negative sign, what I'm going to use then is that I'm going to use an inverting op amp. And that inverting op amp has to have that ground at that one spot. But some of you from yesterday's lab may remember this inverting one, and what it does here is it comes in and it does this thing here. It has another feedback resistor, and then I end up having, it doesn't really matter where I put it. I think I come in like this, and then I could call this 1. So then when I look at the output here, it's minus RF, R1, times whatever that input voltage is, which I'll call this V1. So what am I going to do? I'm going to sum these two voltages using the summing amplifier, but I get that negative sign. How do I get rid of that negative sign? I then run it through an inverting op amp, which then is going to reverse the sign here. So let's do this here. So I want to keep the -2 here, but I want to change the sign of this guy. So that means, I think what I said earlier, I said V2, but I made a mistake. I should have done that. So what you'll find here is that I'm going to take one of these, and I'm not going to make it V2, I'm going to make it V1, just because I need to make that positive. So let's do this thing. So the first thing that I can do here, remember, there's a lot of ways to do this. How about if I start with this guy first? And I want to get this guy to be what? A gain of 5. So I got to pick these two resistors such that I get a gain of 5. So here I go. So here's the first stage. That means I'm going to get -5 V1. Okay? So if I do that, here I go. So then I'm going to start here. Here's V1. And then this is, and then I have my feedback resistor. I'm going to make this a little bit higher. And so this guy now, I need to make this guy -5 V1. So if I do that, I can pick any ones I want. About 100K and 20K. So if I have 120K, then that means automatically that I'm going to get the ratio of 120. So then that gives me that. Okay? So now, this is what I'm going to call, I'm going to keep following this line here, and then I'm going to do what? I'm going to throw them right into this guy now. So if I throw them into this guy here, it's coming in, and then here I go. So then I need R1. I keep calling this R1. How about if I call that R2, just to keep that separated? So that means over here, I set R1 equal to 20K, and then how about if we call this RF1, I set to 100K. So I'm going to call that 1, I'm going to call that 1 because that's the first amplifier. Now, if I look at the second one here, now I'm going to bring in my V2 because I'm going to sum these two. So now I need new resistors here, so I'm going to call this R3. They come in, and you can see that they're hitting that one line right there. So then if it hits that one line, I'm going to get minus, positive, and it's important that that ground will be connected to the positive. And then I have sort of like the feedback resistor of 2. And of course, this is then the output that I'm actually going off after right there. Yes?
Is there any reason to use 100K and 20K instead of 5 ohms and 1 ohm?
Okay, let's change that to 5 ohms and 1 ohm. Actually, we already voted, maybe not. No, it's arbitrary. As long as I get the gain of 5. And then, so what I need is I need this output to be this right here. So that means I got to set the gain of 3 and RF to be 2. So that means I got to set RF and R3 to be 2 here. So since he talked about, 5K and 1K, how about if we make this 2K and 1K? So now I got that. So now I'm going to come in, I'm going to call this 1K, and I'm going to call this 2K. So then, when I look at, to get 5 here, now note this guy's going to automatically invert the sign. So we don't want to switch the value of 5 anymore. So if I call that 2K, we need this guy to be 1. And the only way we can get 1, once I fix that, then that means it's got to be 2K. So now, that tells me that this guy has to be 2K. So now if I come in to my summing amplifier here, you can see that the way I got that here is it was minus, and then I had what? I had RF2 R1 times RF2 divided by R2 divided times V2 plus RF2 R3 V2. And so when I plug these guys in, I can see that I'm going to get minus, and then this guy comes in at minus 5. Damn it. Okay, that's a little bit better. And then I get this guy of 2 times V2, which then gives me an answer of 5V1 minus 2V2. So all I did here is I played Legos with op amps to get them to give me that. Right? There's not a lot of difference between that and this. And just
Does the summing op amp have to be inverted?
the way this one is. You'll see that the non-inverting one's a little bit more complicated. But I could have used that one.
Yeah.
Yeah, I mean, the only reason I picked this one is because it's multiple stage, you're seeing where I'm going. But, by the way, could I have reversed this? No. Because then I would get, if I just started with this, I would get negative 5V1 and negative V1. So I had to throw in this stage first in order to make that the combination. And that's exactly what I'm asking you to do in the lab. You'll see that on Friday's lab, you're going to do this circuit in a very similar way, where you're sort of like designing and you're trying to see where you get what I call clipping or voltage saturation. There's another example, but I think I'm going to stop. I think we need to move on to the next chapter. So that means on Monday we have a problem set here and a quiz on this chapter. Okay, here we go. So guess what? To a large extent, mesh and node are not valid anymore. There's no more, warm, fuzzy feelings when you solve circuits that make you feel like you're actually smart, huh? I mean, there was somebody that I talked to about 2 weeks ago, and he was like, I'm really digging this. I mean, I actually calculate these things, and I get the right answer really easily. I'm going like, yeah, enjoy for 2 more weeks. So now, we are in a completely different arena. You know, mesh and node plays a very important role. And the reason why mesh and node play such an important role is that you figure out very quickly that if you're not careful, man, all shit breaks loose, right? This little sign, you're going, God damn it, I can't get the answer. PSpice gives me this, Cardinals gives you this, but I can't get that answer. It's only when you are a master of signs can you deal with all of the stuff that you have to do. Now, we go to a different process. You'll see what we're moving towards is the differential equations part of this course. And why can't we do mesh and node anymore? It's because when you look at capacitors and inductors, they're not linear. Right? So if we look at linear circuits here, so if you look at linear circuits, we saw here that the voltage was directly connected to that. So this effect